Dear students, in this class I am going to discuss the important properties and phenomena exhibited by moving charges and current carrying conductors. In the chapter Electric Charges and Fields, we discuss one of the important properties of electric charge. That is, a stationary charge produces only electric field, whereas a charge in motion produces both electric as well as magnetic fields. Not only moving charges, even a current carrying conductor produces a magnetic field around it. This was first demonstrated by Oyster. He noticed that when a current carrying conductor is placed close to a magnetic needle, it undergoes a deflection. This proves beyond doubt that a current carrying conductor produces a magnetic field around it. Okay. This can also be demonstrated with another simple experiment. Take a cardboard, arrange it in the horizontal plane, make a small hole at the center. Allow a conductor to pass through it. Sprinkle iron filings on this cardboard. Now current is allowed to flow through this conductor. Here the direction of flow of current is perpendicular to the plane in which the cardboard is present. Now current is flowing through the conductor, and if you gently tap the cardboard, these iron filings, they align in the form of concentric circles. Each circle indicates a magnetic field line. Here we notice that this current carrying conductor produces a magnetic field in a plane at right angles to it. And in this magnetic field, the field lines are in the form of concentric circles. One of the properties of a magnetic field line is, for instance, if this is a magnetic field line, if you draw a tangent at a point to this field line, the tangent indicates the direction of magnetic field induction at that point. If you draw a tangent here, it indicates the direction of magnetic field induction at that point. So here also, if you draw a tangent to this, any one of these concentric circles, it indicates the tangent represents the direction of magnetic field induction at that point. Before you draw the tangent to this magnetic field line, first of all, you must ascertain whether this field line is clockwise or counterclockwise. In order to find whether the field lines are clockwise or counterclockwise, you can apply Ampere's right hand thumb rule. According to Ampere's right hand thumb rule, if you hold your right hand in such a way that the thumb points the direction of flow of current, then the direction in which the remaining four fingers curl represent the direction of magnetic field lines. For instance, if the current is in upward direction, so hold your right hand like this, with your thumb indicating the direction of flow of current, which is upwards. Then the direction in which the remaining four fingers curl indicates the direction of magnetic field lines. So in this illustration, the direction of flow of current is upwards. So the field lines are like this. That is counterclockwise. with respect to top U. These field lines are counterclockwise. Once you know the direction of these field lines, you can easily draw tangent at any given point. That tangent indicates the direction of magnetic field induction at that point. Okay? Now, let me elaborate this Ampere's right hand thumb rule. Let us consider a straight conductor carrying current in upward direction. This straight conductor is carrying current in the upward direction. Now, take this conductor as a reference. This side is taken as north. This is south. This is east. To your left is west. Okay, this is the convention we follow. Anything to the right of this conductor is east. Left side of this conductor, left side with respect to you, is west. Away from you is north. Towards you is south. Now, consider a point to the north of the conductor. That is, if this is the conductor, consider a point to the north of this conductor. Then, imagine yourself holding the conductor like this. Here, field lines, they take a curve like this. At this point, if you draw a tangent, the tangent will be towards west. To your left means towards left. So, the direction of B, magnetic field induction, is towards left, towards west. Now consider a point to the south of the conductor. Magnetic field lines, they curve like this. At this point, if you draw a tangent, it will be towards right. That is towards east. So if the point is to the south of the conductor, the direction of magnetic field induction B is towards east. Now consider a point to the west of the conductor. Imagine a point somewhere here. The field lines, they curve like this. At this point, if you draw a tangent, the tangent will be towards you, that is towards south. So, at a point to the west of the conductor, magnetic field induction B is towards south. Okay. Now consider a point to the east of the conductor. The field lines get curve like this. At this point, if you draw a tangent, the tangent will be directed towards north. So, at a point to the east of the conductor, B is towards north. This is how one can determine the direction of magnetic field induction at any point nearer to a current carrying conductor. Here we assume that the conductor is carrying current in the upward direction. What if the conductor is carrying current in the downward direction? It is the reverse of this. If we consider a point to the north of the conductor, the direction of magnetic field induction is towards east. Instead of west, it is towards east. If you consider a point to the south of the conductor, here, the field lines, they are like this. At this point, if you draw a tangent, it will be towards west. Similarly, at a point to the west of the conductor, the field lines are like this. If you draw a tangent, the tangent will be towards north. If the current is upwards, field is towards south, but here it is towards north. If the conductor is carrying current in the downward direction, and if you consider a point to the east of the conductor, the field lines, they are like this. At this point, if you draw a tangent, the tangent will be towards south. Here it is towards north, in this case it is towards south. Okay? Now, let us discuss few more cases. In order to understand or in order to apply this Ampere's right hand thumb rule, let us consider a few more cases. Let us consider a straight conductor carrying current from west to east. West to east. Point relative to the conductor direction of B. Direction of magnetic field induction. So here obviously the conductor is in the horizontal plane. It is like this. This is the straight conductor carrying current from west to east. That is, with respect to you, current is flowing from left to right. Now, consider a point vertically above this conductor. At a point above the conductor, you consider a point like this. At this point, the field lines are like this. At a point above this conductor, if you draw a tangent, it will be towards U. That is, the direction of B is towards south. Consider a point below the conductor. You can easily answer this question. The field lines, they curl like this. At a point below the conductor, what is the direction of magnetic field induction? It is away from you, that is towards north. Okay. Now consider a point to the north of the conductor. somewhere here, the field lines, they curve like this. At this point, if you draw a tangent, the tangent will be vertically up. So at a point to the north of the conductor, magnetic field induction is upwards, vertically up. Now you can easily answer this question. What is the direction of magnetic field induction at a point to the south of the conductor? Here, at this point. The field lines, they curve like this. At this point, if you draw a tangent, it is vertically downwards. At a point to the south of the conductor, the direction of magnetic field induction is downwards. Okay. Later you practice to find the direction of magnetic field induction in case of a straight conductor carrying current from east to west. With the help of this table, you can easily answer that case also. If the conductor is carrying current from east to west, at a point above the conductor, direction of magnetic field is towards north. At a point below the conductor, it is towards south. At a point to the north of the conductor, downwards. At a point to the south of the conductor, it is upwards. Okay. It is the reverse of this. Now, consider another case where the straight conductor is carrying current from south to north. So once again, the conductor is in the horizontal plane. It is carrying current like this towards, from south to north, away from you. The direction of flow of current is from south to north. So imagine yourself holding your right hand like this, the thumb pointing the direction of flow of current. Then the direction in which the four fingers of your right hand curve indicates the direction of magnetic field lines. So here you consider a point vertically above this conductor. At a point above the conductor, this is the conductor carrying current from south to north. If we consider a point above this conductor, the field lines curve like this. At this point, if you draw a tangent, it is to your right, that is towards east. The direction of B is towards east. What about the direction of magnetic field induction at a point below the conductor? At a point below the conductor. Obviously, it is towards west. How about a point to the east of this conductor, that is to the right of this conductor, right side of this conductor. At a point to the east of the conductor, the field lines, they take a curve like this. At this point, if you draw a tangent, It is vertically downwards. So the direction of B is downwards. At a point to the west of the conductor, obviously it is upwards. So these are the various applications of this Ampere's right hand thumb rule used to determine the direction of magnetic field induction at any point nearer to a current carrying conductor. Later in the next session, we will discuss how to determine the location of a magnetic null point nearer to a straight current carrying conductor.